Think you've seen everything Jupiter has to offer? Not even close. After 8 years of close encounters, NASA's Juno spacecraft has returned data so unexpected, so disruptive, that it's forcing scientists to reconsider Jupiter's entire origin story. What lies beneath those familiar bands of swirling clouds isn't just mysterious, it's something no traditional model of gas giant formation predicted. For decades, researchers argued over whether Jupiter hid a solid, compact core beneath its crushing atmosphere, or whether it was simply a colossal sphere of gas without any real center. But Juno's newest findings don't support either idea. Instead, the spacecraft found something radically different. Jupiter's heart is spread out, stretched, dissolved, blurred into the layers above it. Not solid, not hollow. A diffuse interior that behaves nothing like the planets we thought we understood. And this discovery doesn't just rewrite Jupiter's story, it threatens to break every model we've ever used to explain giant planets across the universe. To understand how Juno uncovered this astonishing truth, you need to understand just how precisely the spacecraft moves. Orbiting Jupiter in a long, looping polar path, Juno swoops closer than any mission in history, skimming just a few thousand kilometers above the cloud tops. At those altitudes, Jupiter's immense gravity tugs on the spacecraft with incredible strength. Every tiny acceleration or deceleration affects the radio signal Juno beams back to Earth. By measuring the exact frequency of that signal, scientists can detect the slightest irregularities in Jupiter's gravitational pull. Irregularities caused by the distribution of mass deep inside the planet. And with each pass, the story became stranger. The gravitational field didn't match a planet with a solid core. But it didn't match a coreless world either. Instead, it pointed to a vast inner region where heavy materials gradually mix into lighter hydrogen, creating no clear boundary, no sharp transition. A core that behaves like a ghost, present yet dispersed. This discovery raises a question that cuts right to the heart of planetary science. How can a giant planet form something so strange? To find answers, scientists first turn to Jupiter's earliest days. One idea suggests the young Jupiter might once have had a dense, rocky center, the classic seed core needed to gather gas from the early solar nebula. But something happened to that seed, something powerful enough to tear it apart and blend it with the upper layers. The most dramatic explanation is a giant collision. A protoplanet crashing into Jupiter with devastating force, breaking apart its solid interior and scattering the heavy elements outward. But when researchers tried to simulate such an event, the results didn't match Juno's data. In every model, the heavy materials eventually fell back inward and reformed a compact core. Juno, however, showed a blurred interior extending through almost half the planet's radius. So if a collision can't explain it, what can? Another possibility is that Jupiter formed much faster than expected, drawing in gas before its inner materials had time to settle. In that scenario, heat and turbulence would have stirred the early interior, stretching and diluting the core before it ever had a chance to harden. But this theory also struggles to explain one crucial detail. The gravitational signatures recorded by Juno are too smooth, too consistent, too stable for a structure created by short-lived chaos. Meanwhile, an unexpected source of clues emerged: Saturn. Studies of Saturn's interior now show that it too contains a diffuse, extended region of mixed heavy elements, surprisingly similar to Jupiter's. That means fuzzy cores may not be strange at all. They may be the natural outcome of giant planet evolution. And if that's true, then exoplanets orbiting distant stars, thousands of them already discovered, might share the same internal structures. But Jupiter still refuses to make things simple. Juno's readings of the magnetic field complicate the picture. Jupiter's magnetic field is not only the strongest of any planet in the solar system, it's also wildly uneven. The northern hemisphere produces intense, concentrated magnetic clusters, while the southern hemisphere behaves in a completely different way. Scientists hoped the diffuse core would help explain this imbalance. Instead, it revealed an even bigger mystery. The magnetic data from Juno shows that Jupiter's dynamo, the deep engine generating its magnetic field, isn't operating in a simple, consistent way. Instead, it seems to switch behavior at different depths. Near the metallic hydrogen layer, the magnetic field behaves as expected, powerful, stable, and electrically driven. But deeper down, near the fuzzy core, the field becomes distorted. Something down there disrupts the flow of electrical currents. Something denies the smooth rotational motion that should power Jupiter's magnetic engine. And this is where convection, or rather the lack of it, enters the story. For decades, scientists assumed Jupiter mixed itself from the inside out, with hot material rising and cooler material sinking, just like boiling water. But Juno's readings show large regions inside Jupiter that don't mix at all. They remain stratified, locked in place by differences in composition and temperature. These stable layers prevent the heavy materials from sinking quickly. They also influence how magnetic currents move, twist, or stall. This partially explains why Jupiter's magnetic field is so lopsided, but not entirely. Something else is happening. Some researchers believe that helium rain, droplets of helium separating from hydrogen under extreme pressures, may fall through the metallic layers, altering the flow of energy. Others think Jupiter's interior rotates at different speeds depending on depth. Or perhaps the dilute core itself contains swirling currents we haven't been able to detect. Whatever the cause, one thing is clear. The fuzzy core complicates everything we thought we understood about Jupiter's magnetism, and that has consequences far beyond our solar system. Many exoplanets, known as hot Jupiters, have intense magnetic fields that shape their atmospheres, winds, and temperatures. If their interiors resemble Jupiter's, their magnetic behavior may be just as complex and just as unexpected. As for Jupiter, the more Juno learns, the stranger the planet becomes. Instead of approaching clarity, each discovery opens a new branch of questions. Each orbit reveals a deeper layer of confusion. And every gravitational or magnetic anomaly tells us the same thing. Jupiter is far more dynamic, far more intricate than we ever imagined. Even with 8 years of data, Juno has only begun to uncover what lies beneath Jupiter's furious storms. The spacecraft has shown that the Great Red Spot extends far deeper than expected, that jet streams penetrate thousands of kilometers below the clouds, and that the planet's rotation varies subtly with depth, each finding hints at the complex forces shaping Jupiter's interior. But the greatest mystery is still the core itself. Is the fuzzy core stable, or is it dissolving slowly into the envelope, changing the planet's interior from decade to decade? If the diffuse heart of Jupiter shifts over time, even slightly, that could influence magnetic behavior, heat flow, and even the stability of storms at the surface. The possibility that Jupiter is still evolving internally makes the giant more fascinating than ever. And through all of this, Jupiter continues producing the largest auroras in the solar system. Unlike Earth's fleeting northern lights, Jupiter's polar lights burn constantly, fed by currents flowing through the magnetosphere. These auroras are so powerful that they emit X-rays, a feature unheard of on any rocky world. Juno's ultraviolet images show them shimmering in bright rings, often larger than our entire planet. Yet even these spectacular displays may hold clues about what happens deep inside Jupiter. Subtle pulses in the auroras correspond to changes in the magnetic field, suggesting that interior processes ripple outward into space. The mysteries of Jupiter's heart, in other words, can be read at its poles. But despite everything Juno has accomplished, many questions remain unanswered. How exactly did Jupiter's core become diffuse? How stable are the interior layers? What role does helium rain truly play? And will future missions reveal a slow drift in Jupiter's interior structure as time passes? One thing is certain. Juno has transformed Jupiter from a familiar gas giant into one of the most complex laboratories in the solar system. What it has revealed, from the diffuse core to the fractured magnetic field, marks just the beginning of a deeper journey into understanding how planets form, evolve, and behave. The more we uncover, the more Jupiter proves that the largest planet in our system is also one of the most unpredictable. And that's why we're not done exploring.